Welcome back. All right, so continuing on, we're going to now solve the following problem. All right, so g of x equals x squared plus 1 divided by x squared minus 4. All right, so we want to find where the function is concave up, concave down, and find inflection points. And to do that, we need to take the second derivative. All right, so our first step, take the first derivative and then the second derivative. And this is a quotient, so we'll use the quotient rule. The numerator is x squared plus 1. The derivative is 2x. The denominator is x squared minus 4. The derivative is also 2x. Right, so the derivative here, g prime of x, would be the denominator times the derivative of the numerator, so 2x times x squared minus 4, minus the numerator times the derivative of the denominator, so minus 2x times x squared plus 1. All right, all over. Excuse me, got a tickle in my throat. The denominator squared, so x squared minus 4 squared. All right, so let's simplify this. As soon as you get a tickle in your throat, you can't help but keep coughing. There we go. So g prime of x is equal to, we could pull out the 2x, and then we'd have, and then we get a lot simpler. We'd have x squared minus 4, and then we need to distribute that negative, right? So the negative gets distributed to the x squared plus 1. Right, so be careful with this when you're simplifying. We have to distribute the, I can factor out the 2x, but I would still need to distribute the negative, right? Because 2x times negative 1 would equal negative 2x, and you have to distribute it to both those terms. So parentheses will help you there. And then divided by x squared minus 4 squared. All right, so now let's simplify. So we have g prime of x equals, so this would be 2x times, so this would be x squared minus 4, and this would be plus negative x squared and negative 1. So that's just going to be a negative 5 in the numerator. So that got simpler. Divided by x squared minus 4 all squared. So let's just make that negative 10x. Here's where all the space takes, we need all the space for just taking the derivative. All right, so now we have another quotient rule. So now u is negative 10x. The derivative would be negative 10. The denominator is x squared minus 4 squared. The derivative is going to be 2 times x squared minus 4 times the derivative of the inside. So that would be times 2x. So let's simplify that. 4x times x squared minus 4. I want to just leave it like that. That thing there is a square. There we go. All right, so now second derivative. G double prime of x is the denominator times the derivative of the numerator, so negative 10 times x squared minus 4 squared, minus the denominator, the numerator times the derivative of the denominator. So that would be now plus 10x times 4x times x squared minus 4, all divided by x squared minus 4, now to the 4th power, right? Because x squared minus 4 squared, and we square that, it's x squared minus 4 to the 4th power. Let's clean this up. So g double prime of x equals, let's factor out the negative 10, let's factor out an x squared minus 4. So negative 10 times x squared minus 4. That'll leave, in the first term, an x squared minus 4. In the second term, we'll have plus, and so excuse me, minus, because we factored out a negative 10, so that's now minus. Minus x times 4x times nothing, right? Because the x squared minus 4 is already factored out. Probably should do that. Close my brackets. All divided by x squared minus 4 to the 4th. So pays to take your time when you're simplifying so you don't make a careless error that just makes everything wrong. All right, so let's simplify our terms. This right here is going to be a negative 4x squared. So that's going to be negative 3x squared minus 4. And we could cancel out this, right, and make that cubed. So we have negative 10 times negative 3x squared. That's going to be negative 30x squared in the numerator, and in the denominator, x squared minus 4 cubed. There we go. All right, so that was all step 1. Whew. Step 2, I'm going to change colors. Maybe that'll help it make it clear. Well, where's step 1 and where's step 2 and where's step 3? All right, so step 2, we're looking for where the derivative is either 0 or undefined. All right, so it's 0. Well, this is a pretty easy solve. We set the numerator equal to 0. That's where double prime of x equals 0 is where the numerator equals 0. So, well, that is at 0. That's not very difficult. And then where the derivative is undefined is going to be where the denominator equals 0. So if we were to take the cube root of both sides, I'll switch colors, cube root, right? We'd have x squared minus 4 equals 0, and of course that factors, and that means we have 2 places where the derivative is undefined. That is also where the function is undefined, right? So it could still be, we could still have a change in concavity, right? But these won't be inflection points. The only possible inflection point is the 0. All right, so let's do the sign chart. So that would be, this was step 2, finding our possible critical points for the second derivative. Well, not our possible. They are critical points for the second derivative. They are possible inflection points. Now we'll do the sign chart, and we'll still include the 2 and the negative 2, even though they can't be inflection points. Right, so here is where the second derivative is 0. Here it's undefined. And then negative 1 and 1, and negative 3 and 3. So we've got points on either side of all of these critical points. Right? And then we have to plug that in. I may not write everything down, right? Because I think we could plug in, here's our second derivative. Right? I think we could plug into that in our, well, just to make sure you're following along, since you're watching this and I can't look at your faces and see if you're understanding. I will write it down, but I'll try not to, try to write just the minimum here. All right, so in the numerator, if I plug in a negative 3, that's going to be negative 3 squared, which is 9, times negative 30, that's negative 270. So that's negative in the numerator. And actually, we didn't even have to write down the 270. We could just write down the negative. Negative in the numerator. How about the denominator? Right? So negative 3 squared is 9. 9 minus 4 is 5. 5 cubed is positive. Right? So a negative and a positive, this is negative. There we go. We're writing down the minimum here. Oops, not f of negative 2. We know that's undefined. F of negative 1. All right, so that would be negative 1 squared times, that'd be 1 times negative 30. That is negative. And then negative 1 squared is 1. 1 minus 4 is negative 3. Negative 3 cubed is negative. So that interval is positive. All right, so we do have a change in concavity at negative 2, even though it is not a inflection point, because it doesn't exist. The function does not exist at negative 2 and 2. It has vertical asymptotes there. All right, so f of 1, all right, that would be 1 squared, which is 1 times negative 30, that is negative. You plug in 1 squared, that's 1 minus 4, that's negative 3. That's going to be negative, right? So still positive. right? So 0 is nothing, right? Not an inflection point. This has no inflection points. And then f of 3, that's going to be negative on the top and positive on the denominator. It's going to be the exact same thing as you got for positive 3. Right? So that is concave up. All right, so now let's do step 4. And step 4 is the interpretation. So actually, this is not f of x, this is g of x. I don't know why I put f's over here. I guess I forgot the name of the function. This is g. Yeah, don't do that on the AP test. You got to name the function by what it's called. So g's. Okay, so step 4 is to interpret. So g of x is concave. I'll start with concave up. Concave up from negative 1, actually, excuse me, negative 2 to 0. Right? And we do have, even though it's not an inflection point, right, it was a critical point for the second derivative. Don't make that make that 2 parts, all right? So negative 2 to 0, and then 0 to 2. It still stays concave up, and then, oops. In my sign chart, I put a plus instead of a minus. I put a minus and plus over here. You knew I meant minus. All right, so g of x is concave up, negative 2 to 0, 0 to 2, because g double prime of x is greater than 0. That's not right, is. Let's just put greater than 0 on the interval. Actually, let's be really specific. That this interval, g of x is concave down. Missing a word there. On negative infinity to negative 2. And 2 to infinity, because g double prime of x is less than 0 on this interval. G of x changes concavity at negative 2 and 2, but these are not inflection points. No S there, just inflection. Not inflection points, because g of x does not exist. Actually, let's put g of 2 and g of negative 2 does not exist, rather than saying g of x does not exist at negative 2. Let's put g of negative 2 does not exist, and g of 2 does not exist. All right, those are not, they can't be inflection points if they're not in the domain of the function, right? So we can actually put in little parentheses there, not in domain of g of x. Or if you want to be fancy mathematical, make sure you can see everything. Fancy mathematical, you can put that negative 2 and 2, so this is an element, not an element in G. So it just says negative 2 and 2, not an element is what that means in G. And that just means G of x. You can call it G, right? Or you can call it G of x. All right, so we found where it's concave up and concave down. I took much space to do so, but it has no inflection points because it changes at where the function is discontinuous. And you can have changes in concavity at points of discontinuity or things that make the function discontinuous, like an asymptote. This is typed and it's in your notes, so I saw no point in untyping it. So this is me reading. All right, so we have f of x, and this is my typing. Isn't it beautiful? I even typed a sign chart. F of x equals x to the fourth minus 4x cubed, doing the same thing, looking for the inflection points. I didn't put in the points, I just put in the x value, but we'll read through what I wrote. All right, so f of x equals x to the fourth minus 4x cubed. First derivative, 4x cubed minus 12x squared, just a little power rule. Second derivative, one more power rule, right? So we got 3 times 4, 12x, now squared, minus 12 times 2, 24x. Set that equal to 0. Nice, easy derivative here, nice, easy solve. Factor out the 12x, set them both equal to 0, so x is 0 and x is 2. Got your sign chart here. You plug the values around where the second derivative is 0 into the second derivative. All right, so this would be f double prime of negative 1, f double prime of 1, and f double prime of 3. All right, so you plug negative 1, you'd have, I like to plug it back into the factored one, right? Because I don't care about the value, I just care about the sign. So you have a negative, and times a negative, that's going to be a positive. You plug in the 1, you got a positive times a negative, that's negative. You plug in the 3, you got a positive times a positive, and that's positive. Right? And it looks like I showed the plugging in down here too. Didn't really need to. But this one here was a positive 36. Oh. When we plugged in the negative 1. When you plug in the 1, you get negative 12. And when you plug in the 3, you get a positive 36. Right? And so f of x, for x less than 0, f of x is concave up. Right? So I wrote it this way, as long as possible, or I could have just said negative infinity to 0. Right? So I put x less than 0, or I could put negative infinity to 0. Either is fine. F of x is concave up because f double prime of x is positive. There's an inflection point at x equals 0 because f double x is positive from negative infinity to 0 and negative from 0 to 2. So in other words, it changes sign. And let's actually write the full point, not just the x value. So to find the actual point, we have to plug it back into the original function. So this would be f of 0. And that would just be 0. Right? So changes sign at 0, 0. From 0 to 2, f of x is concave down because f double prime of x is negative. There's an inflection point at x equals 2. And specifically, that would be f of 2. That would be 2 to the 4th minus, I need a little bit more space, 4 times 2 cubed. There we go. That's going to be, boy, here, we'll get rid of the arrow. There we go. That's going to be 16 minus, that would be 8 times 4. That'd be 32, so that's negative 16. So this is the point 2, negative 16. So the inflection points are at 0, 0, and 2, negative 16, because that's an S. F double prime of x changes signs at these values. And so there's more than one way to say the same thing, so long as you have the correct interpretation, right? The correct information, right? And To be able to know something is an inflection point, you're looking for it to change signs, right? So the function has inflection points where the second derivative changes sign, right? So changes sign at these values, or at these points. So they are the inflection points. Right, I'll continue reading what I typed here, since I typed it so beautifully. There's an inflection point at x equals 2 because that should be f double prime of x. So apparently, fix your notes. I apparently got a little carried away there. Will it go away? Here we go. Typing in quotation marks. I got 3 of them in there. It's the second derivative, not the third. Because f double prime of x is negative from 0 to 2 and positive from 2 to 0. All right, so changes signs at 2. That means 2 is an inflection point. The exact point is 2, negative 16. And we got the negative 16 from plugging 2 back into the original function. And then finally it's concave up from 2 to infinity because f double prime is positive on this interval. Okay? So there we go. Let's do the next one. And I think I typed in these. I got, I guess, into a typing mood. And boy, do I type a lot. And apparently, I can't tell when I type in 2 or 3 apostrophes or quotation marks, whatever the heck those things are called. So just fix it. All right, so here's the second one. Y equals e to the negative x squared. Right, so it's exact copy times the derivative of the exponent. So that'd be negative 2x times e to the negative x squared. Second derivative would be a chain rule. We saw one almost like this one. No, exactly like this one. It just, it had a 2 in front of it. So that would be negative 2x. So it would be the first times the derivative of the second plus the second times the derivative of the first. Right? So the first is negative 2x. The derivative of the second is e to the negative x squared times negative 2x, exactly what we saw on the line above. Plus the derivative of the first one is a negative 2, and then the second term is e to the negative x squared. So we can factor out, we can simplify this. Negative 2x times negative 2x is 4x squared. And then we can factor out the 2 and the e to the negative x squared. Right? So the e to the negative x squared is never 0. Right? This one is going to be positive all the time. So 2x squared minus 1, you can add 1 to both sides, divide by 2, take the square root. And this is very, very similar to another problem we just did in the last video. Right? So we have 2 critical points, the square root of 2 over 2, and negative square root of 2 over 2. Right? And then we just plug those back in. So it really only matters where 2x squared minus 1 is positive and negative, because the other one's always positive. So you plug in a negative 1, you'd have negative 1 squared is 1, and that'd be 2 minus 1, which is 1, which is positive. Plug in a 0, you have negative 1. You plug in 1, you got the exact same thing as you got for negative 1. So for the second derivative is less than 0 for x, where 2x squared minus 1 is less than 0. So wherever that's negative, the second derivative is negative. For x less than 0, f of x is concave up because f double prime of x is positive. There's an inflection point at x equals negative 2 square root of 2. And I actually put the exact inflection points in. I plugged them in right up here, and you got the same thing whether you plug in the negative or the positive. So the exact point is negative square root of 2 over 2, and then 1 over the square root of e. And then f double prime of x is positive, and then we have that inflection point because it changes from positive, from negative infinity to negative 2 square roots of 2 to negative at negative 2 square roots of 2. Right? So change in sign means we're going to have an inflection point. From negative 2 square roots of 2 to 2 square roots of 2, f of x is concave down because f double prime of x is negative. there's an inflection point at x equals the square root of 2 over 2 because f double prime of x is negative from negative 2 square roots of 2 to 2 square roots of 2 and positive from 2 square roots of 2 to infinity. Right? So because f of x double prime of x is positive from the square root of 2 to 2, square root of 2 over 2 to infinity, f of x is concave up. Right? So this one, I guess because I was typing, I was a little wordier. So long as you've made it clear on the sign of this, that you're talking about the second derivative, that when its sign is positive, the original function is concave up. When the sign of the second derivative is negative, the original function is concave down. And that the inflection points occur where the second derivative changes sign. Right? So those are the key things. And there's more than one way to say it. Here's a nice, very complete, no one could argue with, wordy way. Make sure, though, you are precise when you're explaining. And the last one, oh, what an easy, easy, easy one to do. G of x equals x to the fourth. First derivative 4x cubed. Second derivative 12x squared. Set it equal to 0. One critical point at 0. And it's always positive. You plug in negative 1 to the fourth, negative 1 square. We're plugging into the second derivative, right? So this would be, no, sorry, it's g. I just don't want g's. I guess I just like f's. So this would be g double prime of negative 1. That's 1. And g double prime of positive 1 is also 1, right? It's just 1 squared. You can put that in. 1 squared, which is 1. And, excuse me, negative 1 squared, which is 1. And this would be 1 squared, which is 1. So for all values of f of x is concave up because f double prime of x is always positive. 0 is not an inflection point because there's no change in sign for f double prime of x at either side of the critical point. Right? So it's a critical point, but not an inflection point. Nothing at all. Let's see how many more we have. Not too many more. And this is the typing version. These are all in your notes. It looks, did I put them all in? Looks like it. And we only got a couple more of these problems before this video ends. All right, so we have f of x equals the cube root of x. You need to change that to x to the 1/3. The derivative would be 1/3 x to the negative 2/3. The second derivative, another power rule, would be negative 2/3 times 1/3. So that's negative 2/9, and then reduce the exponent by 1 again. So that would be negative 2/9 times x to the negative 5/3. Simplify that negative exponent. You have negative 2 divided by 9x to the 5/3 power. It's never 0, right? But it is undefined when. So if I plug in 0 here, make sure that is clear. So f double prime of, we set that equal to 0. 0 equals negative 2, 9x to the 5/3. Never equals 0, right? Because that would mean negative 2 would have to equal 0. So f double prime of x never equals 0. However, f double prime of x is undefined when x equals 0. All right, so doesn't mean it can't be an inflection point. Just means that it's not defined for the second derivative because it's not a problem for the original function. You can plug in 0 into the cube root of x. All right, so second derivative is never 0. It's undefined when x equals 0. For x less than 0, and we have, where's my oh, I don't see a sign chart. Let's do the sign chart. Right, so make sure you put in the writing parts in your notes. Let's do, oh, well, here it is. Here's the sign chart. It's hidden up here. This is probably already in your notes. All right, so when you plug in negative 1 back into the second derivative, you get negative divided by a negative, so that's positive. When you plug in 1, you get a negative divided by 1 because 1 to any power is 1. And so you'd have negative 2 divided by 9. All right, so for x less than 0, f of x is concave up because x double prime of x, f double prime of x is positive. There's an inflection point at x equals 0 because f double prime of x is positive from negative infinity to 0 and negative from 0 to infinity. Change in sign for the second derivative means inflection point. Right? And the actual point is 0, 0. If you plug 0 into the cube root of 0, you get 0. Right? From 0 to infinity, f of x is concave down because f double prime of x is negative. So there we go. All right? This one, nice, easy one. And the piecewise function there. So the piecewise function, you got to take the derivative of each part separately. Right? So we have the derivative of the numerator of the first part, the first piece, negative 1/2. We have x, negative x to the 1/2 power, which becomes negative 1/2. There are too many negatives in there because it would be 1/2 times negative x to the negative 1/2. Oh, and then times the negative 1. Never mind. There's 2 negatives in there. I don't know. Something is bothering me about my typing. So let me just make sure. So negative x to the 1/2 power would be 1/2 times negative x to the negative 1/2 power times negative 1, the derivative of the inside. Okay, looks good. So negative 1/2, that ends up being negative, I didn't bother to simplify it, but negative 1/2, and then this is in the parentheses, negative x to the negative 1/2 power. We take the second derivative, so now we have negative 1/2 times negative 1/2, which is positive 1/4. But then we have to multiply it times the derivative of the inside. Let me write it down for you. So here was the first derivative. Here was the second derivative. Actually, instead of dy, I'll put y prime. So the second one would be negative 1/2 times the negative 1/2 times negative x to the negative 3/2 power, and then times the derivative of the inside, which is negative 1. So that does make that negative 1/4, because there's an odd number, and that's negative x to the negative 3/2. And then we can simplify that at this point. So we have negative 1/4 times negative x to the 3/2 power. Second derivative is never 0, but it's undefined when x equals 0. And it is not undefined in the original function. So f double prime of x never equals 0. It's undefined when x equals 0. And then we do our sign chart, which is right here. And by the way, the two parts meet. I should add that in there. You can add that to your notes. These two parts intersect at 0, 0. They have to intersect. If they don't, then we couldn't take the derivative. Right? You can't take the derivative, right, if a function's not continuous. So this is a continuous function. All right? So we do the sign chart. If we plug in negative 1, that's going to end up being a negative number because you have a negative divided by a positive. If you plug in positive 1, you end up having a negative divided by a negative. All right. So we have for f of x less than 0, f of x is concave down because f double prime of x is negative. There's an inflection point at x equals 0 because there's no problem for the original function. Because f double prime of x is 0 from negative infinity to 0. and positive from 0 to infinity. From 0 to infinity, f of x is concave up because f double prime of x is positive. The inflection point at f of 0 would be 0, 0, right? We'd plug it in to, really we'd plug it into the negative square root of x because that's for x less than or equal to 0, but it wouldn't make a difference, right? Because it's continuous. Right? So our graph is continuous. There's a cusp at 0, 0. You have two different curves meeting together. Okay? And this is the end of my video. All right? So come back for the next Near Pod and we'll learn to do more things with the second derivative. Bye for now.